What if the universe held secrets so profound that discovering them would fundamentally change how we see our place in existence? Prepare for an expedition through the cosmos' most enigmatic realms where physics bends, time warps, and emptiness itself tells a story. The frozen guardian at the solar system's edge. Far beyond Neptune's orbit, where sunlight becomes a distant whisper, dwarf planet Pluto continues its eternal dance around our star. This celestial enigma, smaller than Earth's moon yet holding secrets that rival any planet, serves as our gateway to the unknown. Positioned roughly 40 astronomical units from the Sun, Pluto follows an eccentric path that takes 248 Earth years to complete. Its diminutive size, with a radius of just 1,188 kilometers, initially fooled astronomers about its true nature. With a mass only 18% that of our Moon, weighing approximately 1.3 times 10 superscript 2 superscript 2 kilograms, Pluto proved to be more asteroid than planet, leading to its controversial reclassification as a dwarf planet in 2006. The dwarf planet's elongated trajectory creates a fascinating orbital dance. In 1989, Pluto reached perihelion, its closest approach to the Sun at 29.7 astronomical units. Since then, the distance has continuously increased and will reach its maximum of 49.3 astronomical units in 2113. This extreme orbital variation means Pluto's distance from the Sun changes by nearly 20 astronomical units over its 248-year orbit. At such vast distances, Pluto remains invisible to the naked eye and appears as merely a murky brown disk even in Hubble Space Telescope images. To unlock its secrets, NASA launched the New Horizons probe in 2006, beginning a 9.5-year journey to the outer solar system. The spacecraft's epic voyage took it past Jupiter, capturing stunning images of the gas giant, before finally reaching its primary target in 2015. When New Horizons finally reached Pluto after a decade-long journey, it revealed a world that defied expectations. The spacecraft made approximately 400 observations during its flyby, collecting over 6 gigabytes of data that took more than a year to transmit back to Earth. Unfortunately, the probe's trajectory prevented it from photographing Pluto's entire surface, as it continued past the dwarf planet to explore other Kuiper belt objects. The mission revealed Pluto's fascinating internal structure. According to current models, the dwarf planet possesses a massive core approximately 1,700 kilometers in diameter, composed of mixed water ice and rocky materials. This core is surrounded by a 300-kilometer thick ice mantle, where poorly understood tectonic processes may be occurring. The outermost layer consists of a crust made from crystallized gases including nitrogen, methane, and carbon monoxide. Scientists theorize that Pluto's core generates sufficient heat to partially melt the icy mantle, potentially creating a subsurface ocean deep beneath the surface. This hypothetical ocean would be extremely salty and toxic, containing large amounts of dissolved ammonia that acts as antifreeze. Such hidden oceans have become a recurring theme in outer solar system exploration, discovered beneath the icy shells of several moons. The spacecraft's cameras captured something extraordinary, a heart-shaped region called Tombaugh Regio, stretching across nearly a quarter of Pluto's surface. This cosmic valentine measures 2,300 kilometers across, making it comparable in size to the entire western United States. Within this heart lies Sputnik Planitia, a smooth nitrogen ice plain spanning 1,492 kilometers that reflects up to 90% of incoming light, making it one of the brightest surfaces in the solar system. This brilliant surface tells the story of a violent past collision that may have unleashed a hidden ocean from Pluto's depths. The plane's convection cell patterns, smooth areas 20 to 30 kilometers across bordered by hills and depressions, suggest active geological processes driven by internal heat. These cellular structures resemble convection patterns in heated fluids, providing indirect evidence for Pluto's warm interior and the potential subsurface ocean. Surrounding this frozen sea rise the Hillary and Tenzing mountain ranges, named after the famous Mount Everest climbers. Some peaks tower 6.5 kilometers above the surface, their water ice composition as hard as solid rock in Pluto's frigid -213 degrees Celsius environment. The western Hillary Mountains reach 3.5 kilometers in height, while the southern Tenzing Mountains include the tallest peaks found on Pluto. The eastern regions paint a different picture entirely. Dark, crater-scarred terrain speaks of ancient bombardments, indicating this area is far older than the smooth western plains. Mysterious dark spots called maculae stretch along the equator like cosmic bruises, named after dark deities from various cultures. The largest, Cthulhu Macula, spans nearly 3,000 kilometers and reflects less than 30% of incident light, creating a stark contrast with nearby bright plains. The dark coloration of these maculae likely results from high concentrations of tholins, complex organic molecules formed when methane and nitrogen are exposed to radiation. The abundance of impact craters in these regions indicates they are remarkably ancient, possibly dating back billions of years to the solar system's violent youth. Moving north from the equatorial dark regions leads to Lowell Regio, a vast valley surrounding Pluto's North Pole. Surprisingly, this polar region currently receives the most illumination on Pluto's surface due to the dwarf planet's extreme axial tilt. Pluto's rotational axis tilts dramatically with respect to its orbital plane, causing it to face the Sun with different hemispheres during its long orbital journey. This unusual orientation has dramatic atmospheric consequences. Over the past 30 years, Pluto's thin atmosphere has tripled in density despite the increasing distance from the Sun. Solar radiation evaporates nitrogen ice deposits at the currently illuminated pole, releasing gas into the atmosphere. This process creates a seasonal cycle spanning decades, as different regions experience their brief summers during Pluto's 248-year orbit. But Pluto's most captivating feature might be its relationship with Charon, its largest moon. With a mass of 1.52 times 10 superscript 2 superscript 1 kilograms, 11% that of Pluto itself, Charon creates a true binary system where both bodies orbit their shared center of gravity. This gravitational partnership causes both objects to be tidally locked, eternally showing the same faces to each other as they complete their orbital dance every 6.4 Earth days. The mass ratio between Pluto and Charon is unique in the solar system. While other planets possess large moons, none approach the relative size of Charon compared to its primary. This unusual relationship causes both objects to wobble around their common center of mass, which lies in the space between them rather than inside either body. Charon's surface differs markedly from Pluto's. The Moon appears noticeably darker overall, with abundant water ice mixed with methane and nitrogen only in certain regions. Its terrain features include the vast Vulcan Planum region, covering at least 400,000 square kilometers, comparable to the size of an average European country. Rising from this plain is Kuiper Mons, a mysterious mountain 40 kilometers across and possibly 4,000 meters tall, surrounded by a circular moat up to 2 kilometers deep. Scientists theorize that Kuiper Mons might be a cryovolcano, an ice volcano that erupts water, ammonia, or methane instead of molten rock. If correct, the surrounding depression could have formed when underground reservoirs emptied, causing the surface to collapse under its own weight. Such cryovolcanic activity would indicate ongoing geological processes driven by tidal heating from Pluto's gravitational pull. North of Vulcan Planum stretches Terra, a heavily cratered region separated from the southern plains by a system of giant ledges and crevices reaching 1 kilometer in height. The largest canyon, Serenity Chasma, extends 200 kilometers in length with a variable width of 40 to 50 kilometers and depths reaching 7 kilometers. These immense geological features suggest a complex history of tectonic activity and crustal deformation. Near Charon's North Pole lies the giant Mordor Macula, a dark region 475 kilometers in diameter whose origin remains debatable. The leading hypothesis suggests that nitrogen and methane gas escaping from Pluto's atmosphere gets trapped by Charon's gravity and settles at the Moon's poles. Ultraviolet radiation from the Sun then converts these gases into dark tholins, which gradually accumulate in the polar ice and create the observed dark coloration. The Pluto-Charon system includes 4 smaller moons, Nix, Hydra, Kerberos, and Styx, likely captured from the Kuiper belt. Nix and Hydra, discovered in 2005, measure several tens of kilometers across, while the later discovered Kerberos and Styx are smaller, not exceeding 16 kilometers in diameter. These irregular chunks of water ice complete this distant family dancing in the outer solar system's twilight. Unfortunately, New Horizons has long since departed this fascinating system, and with Pluto rapidly receding from Earth, detailed study becomes increasingly difficult. The probe currently lies more than 50 astronomical units from Earth and continues transmitting valuable data about the outer solar system. By 2030, its systems will eventually fail, leaving it to drift alone through interstellar space as a human-made monument to cosmic exploration. Worlds that challenge reality. Beyond our solar system lie planets so bizarre they seem torn from science fiction. Among the thousands of confirmed exoplanets, some display behavior that challenges our understanding of planetary physics and orbital mechanics. These alien worlds operate under conditions so extreme they force astronomers to reconsider fundamental assumptions about planetary formation and evolution. Consider Kepler 413b, the vanishing planet that plays cosmic hide-and-seek with astronomers. Discovered in 2009 when it first transited its parent star, this gas giant initially appeared to be a straightforward exoplanet detection. High-precision calculations revealed a world with 25 times Earth's mass and 40% of Jupiter's radius, orbiting in what seemed like a stable configuration. However, 180 days later, the expected second transit never occurred. The planet had seemingly vanished without explanation, leaving astronomers baffled. Various hypotheses emerged. Perhaps a dark spot on the star's surface or a massive dust cloud had mimicked a planetary transit. But these theories crumbled when the mysterious object reappeared 800 days later, eclipsing its star 5 more times before disappearing again. The solution to this cosmic puzzle lay in Kepler 413b's extraordinary orbital dynamics. This gas giant orbits a binary star system, positioned 36 astronomical units from the common center of mass. The gravitational tug-of-war between two parent stars causes the planet's orbital plane to oscillate dramatically over time. Every 11 years, the orbit tilts up to 2.5 degrees in each direction from its average position, sometimes carrying it completely out of our line of sight. This orbital chaos creates nightmarish climate conditions on the planet's surface. The planet's rotational axis can tilt up to 30 degrees during these oscillations, causing the region receiving maximum stellar radiation to shift constantly from equator to poles and back again. These dramatic changes spawn planetary-scale hurricanes larger than Jupiter's Great Red Spot, with ice clouds hurtling through the atmosphere at several kilometers per second before becoming unstable and dispersing. The atmospheric dynamics become even more extreme during these climate shifts. Massive air currents generate such powerful atmospheric ejections that material can actually escape the planet's gravity and hang temporarily in space before gravitational forces pull it back down. This creates a constantly churning, chaotic environment where weather patterns could reshape entire hemispheres within planetary seasons. Then there's HD 189733b, a world where the very concept of weather becomes apocalyptic. This gas giant, located 190 light-years from Earth, orbits a yellow dwarf star remarkably similar to our Sun. However, its highly eccentric orbit creates the most extreme climate variations known in the galaxy. Every 55 days, this 4-Jupiter-mass planet plunges toward its star like a massive comet, experiencing temperature swings that would make Earth's most extreme weather seem gentle. At its most distant point, 0.88 astronomical units from its star, the planet receives roughly the same amount of solar energy as Earth. During these temperate periods, water vapor clouds might condense in its atmosphere, and temperatures on hypothetical moons could become comparable to Earth's surface conditions. But as the planet races inward, conditions change catastrophically. Within 55 days, the distance shrinks by a factor of nearly 30, and incoming energy flux increases 800-fold. Surface temperatures rocket from 500 degrees Celsius to 1,200 degrees Celsius in just 6 hours, a rate of temperature change that defies comprehension. The atmosphere expands so rapidly it generates shock waves that sweep across the entire planet multiple times, creating a hellscape of supersonic winds reaching 5 kilometers per second. These extreme winds could circle Earth's entire circumference in less than 3 hours. The rapid heating breaks down water vapor into constituent hydrogen and oxygen atoms, while any quartz crystals in the atmosphere completely evaporate before recondensing into gigantic sand clouds during the cooling phase. The planet essentially experiences a complete atmospheric restructuring twice per orbit, making it one of the most dynamically active worlds known to science. Perhaps most unsettling is the Kepler 36 system, where two planets engage in a gravitational death spiral that will inevitably end in cosmic catastrophe. Located 1,530 light-years from Earth, this system orbits a yellow subgiant star 62% larger than our Sun. The two worlds, a rocky super-Earth and a hot mini-Neptune, pursue dangerously close orbits that bring them within 1.9 million kilometers every 97 days. To put this distance in perspective, it's roughly 20 times smaller than the minimum distance between Earth and Venus, and closer than most major moons orbit their parent planets. At these moments of closest approach, their mutual gravitational attraction reaches 13 times the strength of Earth-Moon tidal interactions, triggering global cataclysms on both worlds. The inner planet, Kepler 36b, bears the brunt of these encounters. This rocky super-Earth, with 3.8 times Earth's mass and 1.5 times its radius, experiences surface temperatures of 700 degrees Celsius due to its close proximity to the parent star. During gravitational encounters, titanic tidal forces crack the planet's crust and trigger massive earthquakes that could tear continents apart. The resulting geological chaos creates vast volcanic regions that never cool between encounters, maintaining seas of perpetually molten rock across significant portions of the surface. The outer planet, Kepler 36c, classified as a hot mini-Neptune, possesses 7 times Earth's mass and 3.7 times its radius. This world maintains a thick atmosphere of nitrogen, hydrogen, and helium that gradually transitions into supercritical fluid layers surrounding a solid core. During close encounters, the mini-Neptune's gravity can potentially capture satellites from its rocky companion, while tidal forces may destroy others to form vast asteroid streams spiraling between the two worlds. The gravitational dance between these planets creates chaotic orbital variations that make long-term prediction impossible. Computer modeling reveals a 91% probability that the two worlds will collide within the next 70 million years, a cosmic blink of an eye. The resulting impact will shatter both planets into hundreds of thousands of fragments, creating a debris field that will disperse throughout their stellar system and potentially seed the formation of entirely new worlds from the wreckage. Such tremendous cataclysms may have occurred repeatedly throughout this system's history, explaining the unusual orbital configuration we observe today. The discovery of Kepler 36 demonstrates that planetary systems can evolve in ways far more violent and chaotic than previously imagined, challenging models of planetary formation and long-term stability. Even more extraordinary is the object informally dubbed Super Saturn, located 434 light-years from Earth in the constellation Centaurus. This brown dwarf or massive gas giant, possessing 20 times Jupiter's mass, spins within a ring system that dwarfs anything in our solar system. At approximately 15 to 16 million years old, this young object still actively accretes material and continues forming. Transit observations reveal at least 37 distinct ring structures surrounding the central body. The largest ring extends 6 astronomical units from Super Saturn, comparable to Venus's orbital distance and roughly 640 times larger than Saturn's entire ring system. The total mass of this circumplanetary disk exceeds Earth's mass, making it one of the most massive ring systems ever discovered. Mathematical modeling indicates such structures are inherently unstable and gradually disintegrate over hundreds of millions of years. Some ring material loses orbital velocity and spirals into the central body, while other particles accelerate and escape the system entirely. This constant flux creates a dynamic, ever-changing ring architecture unlike the relatively stable systems observed around our solar system's giant planets. Within this cosmic carousel, a large gap approximately 4 astronomical units from the central body suggests the presence of a massive exomoon clearing its orbital path. Current estimates indicate this hypothetical satellite possesses roughly 80% of Earth's mass, making it one of the largest moons ever detected around any planet. Additional observations hint at least 2 more substantial moons, each with approximately 30% of Earth's mass, orbiting closer to the brown dwarf at 0.25 astronomical units. If these satellites exist, they could potentially host stable climates despite orbiting a brown dwarf rather than a traditional star. Computer simulations incorporating radiation from the parent star, heat flow from the massive central body, and tidal influences suggest surface temperatures on these moons could approach comfortable values for liquid water. The night sky from such a world would be spectacular. The brown dwarf would appear 70 times larger than Earth's full moon, bathing the landscape in a soft, perpetual twilight glow. Vast rings would crisscross the sky from horizon to horizon, creating bands of light that would dwarf any aurora display on Earth. However, the massive central body's tidal forces would also trigger constant geological activity, possibly creating volcanic eruptions and tsunami-like tidal waves hundreds of kilometers wide. The boundary between land and sea could shift by hundreds of kilometers twice per day, creating unique tidal zones unlike anything found on Earth. Unfortunately, such magnificent ring systems prove ephemeral on cosmic timescales. The gravitational interactions that create them also ensure their eventual destruction, meaning future observations may reveal completely different architectures. Within millions of years, this cosmic spectacle will transform beyond recognition, reminding us that even the most magnificent celestial displays represent mere moments in the universe's vast timeline. The lighthouse keepers of deep space. In July 1967, graduate student Jocelyn Bell made a discovery that initially sparked fears of extraterrestrial contact. Her radio telescope at Cambridge University detected perfectly regular pulses emanating from deep space, signals so precise they seemed artificial rather than natural. The discovery team initially designated the source LGM, 1 for little green men, and kept their findings secret for months while investigating whether they had detected alien technology. The signals appeared every 1.337 seconds with clockwork precision, unlike any known natural phenomenon. The team's secrecy stemmed from the extraordinary implications. If confirmed as artificial, these would be the first verified signals from an alien civilization. Additional discoveries of 3 more pulsing sources suggested either multiple alien civilizations or a previously unknown class of natural objects. The truth proved even more extraordinary than alien contact. These were pulsars, the universe's most precise natural timekeepers and among the most extreme objects in existence. These cosmic lighthouses are neutron stars, stellar corpses so dense that a teaspoon of their material would weigh as much as Mount Everest. Born from the gravitational collapse of stars at least 18 to 20 times the Sun's mass, they compress the entire mass of a star into a sphere just 20 kilometers across. The first discovered pulsar, PSRB 1919+21, located 2,283 light-years away in the constellation Vulpecula, became the prototype for understanding these exotic objects. When information about the discovery became public in February 1968, it triggered a revolution in astronomy. By 1969, astronomers had detected 27 similar sources and coined the term pulsar to describe these enigmatic objects. The Soviet Union soon joined the search, discovering pulsar PSR B0943+10 in the constellation Leo. Initial theories proposed that pulsars might indeed be ultra-powerful radio beacons constructed by advanced extraterrestrial civilizations, their regular signals resembling lighthouses sweeping across cosmic distances. However, the sheer number of discoveries and their distribution throughout the galaxy soon convinced astronomers that these must be natural phenomena. Current understanding reveals that pulsar signals result from neutron star rotation combined with powerful magnetic fields. As these stellar remnants spin, they emit narrow beams of radio waves from their magnetic poles. When these beams sweep across Earth during each rotation, we detect regular pulses with clockwork precision. The pulse period directly corresponds to the neutron star's rotation rate, making pulsars extraordinarily accurate cosmic chronometers. By 2008, astronomers had catalogued approximately 1,790 pulsars throughout our galaxy and beyond. These objects typically lie several dozen light-years from the Sun, though some exceed thousands of light-years distance. All serve as powerful sources of pulsed radio emissions, their signals detectable across vast interstellar distances despite the object's small physical size. But pulsars come in multiple varieties with dramatically different properties. Radio pulsars, like the first discoveries, gradually slow down over millions of years as they expend rotational energy on particle emission and magnetic field interactions. These objects typically complete one rotation every few seconds to several tenths of a second, with rotation periods gradually increasing as they age. X-ray pulsars operate under completely different physics. These neutron stars exist in binary systems where they steal material from companion stars through gravitational attraction. The stolen matter forms an accretion disk that spirals inward, heating to millions of degrees and radiating intensely in X-ray wavelengths. Unlike radio pulsars that slow down, X-ray pulsars actually spin faster over time as infalling material adds angular momentum to their rotation. The accretion process creates a feedback mechanism that determines the observed emission characteristics. When material flows steadily from the companion star, the neutron star appears as an X-ray source powered by gravitational energy release. However, when the accretion rate drops, the neutron star's intrinsic magnetic field reasserts control, and the object switches to radio emission mode. The most extreme examples are millisecond pulsars, neutron stars spinning hundreds of times per second with rotation periods measured in milliseconds rather than seconds. These cosmic speed demons result from extended accretion episodes that spin up the neutron star to incredible rotation rates. The fastest known pulsar completes nearly 600 rotations per second, approaching the theoretical maximum before centrifugal forces would tear the neutron star apart. J1023 plus 5038, located 4,500 light-years away, exemplifies this exotic class of objects. With a rotation period of just 1.69 milliseconds, this neutron star completes one full rotation in less than 0.02 of a second. The object exists in a binary system with a companion star twice the Sun's mass, completing mutual orbits every 4.45 hours in one of the most compact stellar systems known. This particular pulsar demonstrates transitional behavior between X-ray and radio emission modes. Initially discovered as a radio pulsar, astronomers noticed its signals regularly fade while X-ray emissions increase. This switching behavior occurs as the accretion rate from the companion star varies over time. When sufficient material flows toward the neutron star, it forms an accretion disk that generates X-ray radiation. When the flow decreases, stellar wind prevents disk formation, and the object reverts to radio emission. Recent observations detected millisecond optical pulsations from J1023 plus 5038, making it the first transitional optical pulsar ever discovered. The optical flashes likely result from high-energy electrons in the neutron star's magnetosphere accelerated to near-light speeds. These particles generate intense radiation across multiple wavelengths, creating a cosmic beacon visible from thousands of light-years away. But even more remarkable is NGC 5907X1, a pulsar so luminous it releases more energy in one rotation than our Sun produces in 3.5 years. Located 50 million light-years away in a distant galaxy, this ultraluminous X-ray source initially baffled astronomers who assumed such intense radiation could only originate from black holes. The discovery that NGC 5907X1 is actually a neutron star revolutionized understanding of pulsar physics. Its incredible luminosity exceeds theoretical limits for neutron star accretion, suggesting unknown physical processes at work. The object's rotation period varies mysteriously, from 1.43 seconds in 2003 to 1.13 seconds in 2014, as if the neutron star somehow changes its fundamental spin rate over time. Current astrophysical models cannot fully explain this object's extreme properties. Scientists theorize it may possess a complex multipolar magnetic field that channels accreting matter in ways not yet understood. Alternatively, the neutron star might have an unusually strong magnetic field that creates conditions allowing super-Eddington accretion rates far exceeding normal theoretical limits. The study of pulsars has revealed that neutron stars represent some of the most extreme physics laboratories in the universe. Their surfaces experience gravitational fields billions of times stronger than Earth's, while their interiors may contain exotic matter states impossible to create in terrestrial laboratories. Some theories suggest neutron star cores might contain quark matter or even more exotic forms of matter that exist nowhere else in the cosmos. These cosmic lighthouses also serve as precision tools for testing fundamental physics. Their incredibly stable rotation periods allow astronomers to detect gravitational waves, test general relativity, and search for variations in fundamental constants. The discovery of pulsars orbiting each other has provided direct evidence for gravitational wave emission and confirmed Einstein's predictions about spacetime curvature. As detection technology improves, astronomers continue discovering new pulsar varieties that challenge existing models. Some pulsars exhibit giant radio flares thousands of times brighter than normal, while others display complex emission patterns that suggest magnetic field structures far more complicated than simple dipoles. Each new discovery adds another piece to the puzzle of neutron star physics and the extreme conditions that exist in these cosmic laboratories. Where light goes to die. Black holes represent the universe's ultimate mystery, regions where space and time themselves break down according to Einstein's general relativity. These gravitational monsters form when matter becomes so compressed that nothing, not even light, can escape their gravitational pull. Despite their fearsome reputation and central role in science fiction, black holes remain surprisingly elusive objects that challenge both observation and theoretical understanding. Mathematical modeling suggests our galaxy may contain as many as 100 million black holes scattered throughout its spiral arms and central bulge. However, among the 200 to 400 billion stars in the Milky Way, black holes represent relatively rare cosmic citizens. Their formation requires specific conditions, typically the catastrophic collapse of stars at least 18 to 20 solar masses that exhaust their nuclear fuel and undergo core collapse. The process begins when such massive stars can no longer generate sufficient nuclear pressure to counteract gravitational compression. In a matter of seconds, the stellar core implodes to incredible density while the outer layers explode outward in a supernova that can briefly outshine entire galaxies. If the remaining core exceeds approximately 3 solar masses, the Tolman-Oppenheimer-Fokoff limit, no known force can halt further collapse. What follows defies ordinary description. The collapsing matter crosses the Schwarzschild radius, a spherical boundary where the escape velocity equals the speed of light. Within this event horizon, space and time become so distorted that conventional physics breaks down. The matter itself may collapse to infinite density at a central singularity, though quantum effects might prevent such extreme states through mechanisms we don't yet understand. The closest confirmed black hole to Earth, V616 Monocerotis, lurks just 3,300 light-years away in the constellation Monoceros. This invisible object, containing approximately 6.6 solar masses compressed into a region smaller than Manhattan, orbits with an orange dwarf star every 7.75 hours. The system's existence was revealed through the companion star's orbital motion, which indicates the presence of an unseen massive object far too heavy to be a neutron star. The orange dwarf, stretched and deformed by immense tidal forces, gradually sheds its outer atmospheric layers in spiraling streams of superheated gas. This material forms a brilliant accretion disk that heats to millions of degrees as it spirals inward toward the event horizon. The disk's X-ray emissions allow astronomers to study the black hole's effects on surrounding matter, even though the black hole itself remains invisible. The stellar neighborhood around V616 Monocerotis contains several dozen other stars, some almost certainly hosting their own planetary systems. These worlds exist in the shadow of cosmic catastrophe. Their parent stars will eventually approach the black hole during the galaxy's gravitational evolution. When such encounters occur, stellar systems face complete destruction as tidal forces tear apart planets and redirect stellar material into the accretion disk. Yet contrary to popular belief, black holes aren't cosmic vacuum cleaners that devour everything nearby. From a gravitational perspective, they behave exactly like stars of equivalent mass at distances greater than a few stellar radii. This counterintuitive fact means black holes could theoretically host stable planetary systems, with worlds orbiting safely in zones where tidal forces remain manageable. Such hypothetical planets might form through several mechanisms. Supernova explosions can leave behind debris disks from which new worlds could coalesce, similar to second-generation planet formation around pulsars. Alternatively, black holes might capture rogue planets ejected from other stellar systems, or entire planetary systems could survive when their parent star collapses to form a black hole, provided the orbiting worlds lie sufficiently far from the central catastrophe. The energy source for such worlds would come from the black hole's accretion disk rather than stellar fusion. Material spiraling into the black hole releases enormous amounts of gravitational potential energy, creating luminous disks that could provide heat and light for billions of years. Some theoretical models suggest that planets orbiting within these zones could maintain liquid water on their surfaces, creating the bizarre possibility of life evolving in a black hole's shadow. However, planets venturing too close face inevitable destruction through a process astronomers call spaghettification. The black hole's gravity creates extreme tidal forces that stretch approaching objects along the radial direction while compressing them perpendicular to their motion. Small objects like spacecraft would be torn apart long before reaching the event horizon, while larger bodies like planets could survive closer approaches before disintegration. The resulting debris joins the accretion disk, gradually heating as gravitational potential energy converts to thermal radiation. Material spirals inward over months or years, radiating away orbital energy until it finally crosses the event horizon and disappears from our observable universe. From an external observer's perspective, infalling matter appears to slow down and freeze at the event horizon due to extreme gravitational time dilation, though from the matter's perspective, the journey continues normally. The universe contains three distinct categories of black holes, each representing different formation mechanisms and evolutionary histories. Stellar mass black holes, ranging from 3 to perhaps 50 solar masses, form directly from massive star collapse and represent the most common variety. These objects gradually grow by accreting surrounding matter and occasionally merging with other black holes in spectacular gravitational wave events. Supermassive black holes, containing millions to billions of solar masses, anchor the centers of most galaxies and power the universe's most energetic phenomena. Their formation remains mysterious. They may grow from smaller seed black holes through sustained accretion, or they might form directly from primordial gas clouds in the early universe. When actively feeding, these giants power quasars and active galactic nuclei visible across cosmic distances. The third category, primordial black holes, remains entirely theoretical but could provide crucial insights into the universe's earliest moments. These objects might have formed from density fluctuations in the first fraction of a second after the Big Bang, creating black holes with masses ranging from subatomic particles to thousands of solar masses. Hawking radiation theory predicts that the smallest primordial black holes should be evaporating now, potentially creating detectable gamma-ray signatures. Quantum black holes represent an even more speculative possibility. Theoretical calculations suggest that extremely high-energy particle collisions might create microscopic black holes lasting only tiny fractions of a second before evaporating completely. While such events require energies far beyond current accelerator capabilities, they might occur naturally in cosmic ray interactions with Earth's atmosphere. Detecting black holes requires clever observational techniques since the objects themselves emit no light. Most discoveries result from studying their gravitational effects on visible companions in binary systems. The orbital motion of normal stars can reveal the presence of invisible massive objects, while X-ray emissions from accretion disks provide additional confirmation of black hole candidates. Gravitational microlensing offers another detection method. When a black hole passes between Earth and a background star, its gravity acts as a lens that briefly magnifies the star's light in characteristic ways. This technique has revealed several isolated black holes drifting through the galaxy, though such events require precise alignment and remain relatively rare. The most dramatic black hole discoveries come from gravitational wave detectors like LIGO and Virgo. These instruments can directly sense the spacetime ripples created when black holes spiral into each other and merge. Such observations have revealed a hidden population of stellar mass black holes throughout the universe and confirmed Einstein's predictions about gravitational radiation. Recent technological advances have even allowed direct imaging of black hole event horizons. The Event Horizon Telescope collaboration captured images of the supermassive black holes in galaxies M87 and our own Milky Way, revealing the shadow cast by these objects against their glowing accretion disks. These observations provide the first direct visual evidence of event horizons and confirm many theoretical predictions about black hole structure. As detection methods continue improving, astronomers expect to discover black holes across an enormous range of masses and environmental conditions. Some may harbor exotic matter states or demonstrate quantum gravitational effects that could revolutionize physics. Others might serve as natural laboratories for testing general relativity under the most extreme conditions possible in nature. The study of black holes also illuminates fundamental questions about information, causality, and the nature of spacetime itself. The information paradox, whether information falling into black holes is destroyed or somehow preserved, remains one of theoretical physics' most important unsolved problems. Resolution of this paradox may require new physics that unifies quantum mechanics with general relativity. Perhaps most remarkably, black holes may play essential roles in galaxy formation and evolution. The supermassive giants at galactic centers regulate star formation through powerful outflows and jets, while stellar mass black holes contribute to chemical enrichment through supernova explosions. Rather than cosmic destroyers, black holes may be fundamental architects of the universe's large-scale structure. Galactic wanderers and cosmic collisions. Galaxies, those island universes containing hundreds of billions of stars, engage in their own epic dramas across cosmic time. The vast distances between galaxies, typically millions to billions of light-years, might seem to guarantee eternal isolation, yet gravitational forces orchestrate spectacular encounters over billions of years. These galactic interactions reshape entire stellar populations and drive cosmic evolution on the largest scales. Among the most dramatic examples is Galaxy M86, racing toward us at 244 km per second through the Virgo galaxy cluster. Located 52 million light-years away, this elliptical giant displays a remarkable blue-shifted spectrum indicating approach rather than recession from our cosmic neighborhood. Such motion defies the universe's general expansion and results from complex gravitational dynamics within the massive Virgo cluster. M86's high-speed passage through intergalactic space creates spectacular visual effects. The galaxy's motion through scattered gas within the cluster generates ram pressure that strips away its own interstellar matter, leaving behind glowing trails of ionized hydrogen that stretch for millions of light-years. These luminous filaments connect M86 to nearby NGC 4438, creating bridges of hot gas that mark the galaxy's destructive path through space. The elliptical giant's violent history is written throughout its structure. Stellar streams, ghostly remnants of smaller galaxies consumed over billions of years, thread through M86's outer halo like cosmic archaeology. An impressive collection of over 3,800 globular clusters, roughly 25 times more than the Milky Way possesses, likely represents the surviving cores of destroyed dwarf galaxies. If this interpretation proves correct, M86 may have obliterated tens or hundreds of smaller galactic neighbors during its cosmic rampage through the cluster. This galactic cannibalism continues today. M86's gravitational influence disrupts nearby dwarf galaxies, gradually shredding them and incorporating their stars into its own structure. The process occurs so slowly that individual stellar orbits remain stable, but over millions of years, entire galactic populations merge into the growing elliptical giant. More dramatic still is ESO 137-001, dubbed the Jellyfish Galaxy for its spectacular appearance as it plunges through the Able 3627 galaxy cluster. Located 227 million light-years away with a mass between 5 to 14 billion solar masses, this spiral galaxy races toward the cluster center at nearly 2,000 kilometers per second, faster than many spacecraft achieve during planetary encounters. The immense ram pressure from intergalactic gas within the cluster strips away ESO 137-001's own material with violent efficiency. Gas trails extending 260,000 light-years behind the galaxy, longer than our Milky Way's diameter, contain 2 to 4 times more matter than remains within the galaxy itself. These cosmic tentacles glow with the light of newborn stars, as the stripped gas continues forming stellar nurseries even while torn from its parent galaxy. The spectacle resembles a giant jellyfish floating through endless expanses of space, its tentacles streaming behind as it navigates cosmic currents. Unfortunately, this process dooms the galaxy's future. Without sufficient gas reserves to fuel continued star formation, ESO 137-001 will eventually exhaust its stellar nurseries and fade into a red and dead elliptical remnant populated only by aging stars. Yet this cosmic stripping process provides astronomers with unique opportunities to study dark matter interactions. The galaxy's visible matter experiences drag from intergalactic gas, while its invisible dark matter halo continues unimpeded by such interactions. Observing how these components separate during the stripping process reveals crucial information about dark matter's properties and distribution. Meanwhile, in the distant universe visible 12.2 billion light-years away, the baby boom galaxy demonstrates star formation rates that challenge theoretical understanding. This cosmic nursery creates approximately 4,000 new stars annually, roughly 400 times faster than our own Milky Way's leisurely pace. Simple calculations reveal that on average, a new star ignites somewhere in this galaxy every 2 hours, creating one of the most prolific stellar factories ever discovered. Observing this galaxy provides a window into the universe's youth, showing conditions that existed just 1.5 billion years after the Big Bang, when cosmic structure was still rapidly evolving. During this epoch, galaxies grew through violent processes fundamentally different from the relatively sedate evolution we observe locally. The extraordinary star formation rate in baby boom galaxy may result from massive gas inflows, galactic mergers, or feedback processes that we don't yet fully understand. The galaxy's intense activity cannot continue indefinitely. At current production rates, it would exhaust available gas reserves within a few 100 million years, a brief moment in cosmic time. This suggests we're witnessing a transient phase in galactic evolution, perhaps triggered by a recent merger or gravitational encounter that funneled vast amounts of gas into the galaxy's central regions. The Sombrero Galaxy, M104, presents a different kind of evolutionary puzzle. Located 30 million light-years away with a diameter roughly 4 times smaller than the Milky Way, this object appears to represent two distinct galaxies merged into a single system. Its outer regions display typical spiral structure with prominent dust lanes and star-forming regions, while deeper observations reveal that most stars actually follow elliptical orbits more characteristic of a completely different galaxy type. This dual architecture suggests a violent collision between spiral and elliptical galaxies that occurred billions of years ago. Remarkably, both structural components survived the merger process largely intact, creating the layered galactic architecture we observe today. Computer simulations indicate that such clean mergers require precise collision parameters, specific approach velocities, impact angles, and mass ratios that occur only rarely in cosmic history. The galaxy's massive dust ring, containing most of its young stars, spans thousands of light-years and glows prominently in infrared wavelengths. This structure may represent material disrupted during the ancient merger that eventually settled into a stable ring configuration. Spitzer Space Telescope observations reveal complex dust patterns and star formation regions that continue evolving billions of years after the initial collision. At the Sombrero Galaxy's heart lurks a supermassive black hole exceeding 1 billion solar masses, making it one of the most massive known. This gravitational monster generates powerful X-ray emissions detectable across intergalactic distances, suggesting active accretion of surrounding matter. Several sources of extremely high-frequency terahertz radiation have also been detected within the galaxy, though their exact nature remains mysterious. Perhaps most intriguing is the Black Eye Galaxy, M64, where inner and outer regions rotate in opposite directions like cosmic gears turning against each other. This 25,000 light-year wide spiral, located 17 million light-years away, formed when two smaller galaxies collided at precisely the right angle and velocity to create this extraordinary counter-rotating structure. The galaxy's distinctive appearance results from a dark band of cosmic dust that partially obscures the bright central regions, creating the black eye effect that gives the galaxy its nickname. This dust lane contains young, blue stars that rotate opposite to the galaxy's outer regions, where older, redder stars follow the original rotational pattern. Such counter-rotating systems are extremely rare and require very specific formation conditions. Computer models suggest the progenitor galaxies must have approached at particular angles with carefully matched velocities to create stable counter-rotation rather than complete disruption. The odds of such precise cosmic choreography occurring naturally seem minuscule, yet M64 demonstrates that even the most improbable galactic architectures can arise given enough time and cosmic encounters. The boundary between the two rotating components creates an active star-forming region where gas clouds collide and compress. This cosmic friction zone generates new stellar nurseries at an enhanced rate, creating the bright blue stars that define the dust lane's appearance. Over time, this star formation activity may gradually eliminate the counter-rotation as gas clouds lose angular momentum through repeated collisions. Such galactic encounters will become increasingly common in our cosmic neighborhood as the universe's expansion slows and local gravitational interactions dominate. The Andromeda Galaxy approaches the Milky Way at 110 km per second, promising a spectacular collision in approximately 4.5 billion years. Computer simulations suggest both galaxies will survive the encounter, eventually merging into a single elliptical giant astronomers have dubbed Milkometa. This future merger will dramatically reshape our galactic environment. The solar system will likely survive the collision intact, though our night sky will transform beyond recognition as stellar orbits reorganize and the combined galaxy settles into its new configuration. The merger process itself will span several billion years, creating spectacular stellar streams and triggering massive bursts of star formation as gas clouds collide and compress. Other local group galaxies will also participate in this cosmic restructuring. The Triangulum Galaxy may merge with Andromeda before the Milky Way collision, while numerous dwarf galaxies will either join the central merger or be ejected into intergalactic space by gravitational interactions. The end result will be a fundamentally different cosmic environment where isolated spiral galaxies give way to massive elliptical systems. Understanding galactic collisions provides crucial insights into how the universe's largest structures formed and evolved. Most massive elliptical galaxies likely assembled through multiple merger events over cosmic history, while spiral galaxies like our own represent systems that avoided major disruptions long enough to develop organized disk structures. As astronomers observe galaxy interactions across cosmic time, they piece together the complex history of how simple gas clouds evolved into the diverse galactic zoo we observe today. The architecture of emptiness. Perhaps the most profound discoveries in modern astronomy concern not what fills space, but what doesn't. The universe's large-scale structure resembles a cosmic web, with galaxies strung along filaments separated by vast regions of near-perfect vacuum. These cosmic voids, some spanning hundreds of millions of light-years, contain so little matter they challenge our understanding of how structure formed after the Big Bang. The concept of cosmic emptiness operates on scales almost impossible to comprehend. While interstellar space within galaxies contains roughly 1 hydrogen atom per cubic centimeter, the voids between galaxy superclusters achieve densities thousands of times lower. A photon leaving our Sun could travel to Proxima Centauri, a journey of 4.2 light-years, without encountering a single particle of matter if traveling through such regions. Our cosmic neighborhood sits within one such cavity known as the local void, a roughly spherical depression 150 million light-years in diameter where matter density drops to approximately 20% below the cosmic average. This enormous bubble of emptiness explains several puzzling observations about our galactic environment, including the unusually high velocities of nearby galaxy groups and the relative isolation of the local group. The local void's boundaries are defined by major galaxy concentrations. The Perseus-Pisces supercluster forms one wall, while the Pavo-Indus supercluster creates another. Our own local group, including the Milky Way and Andromeda galaxies, sits on the void's edge along with several hundred other galaxies forming a structure called the local sheet. This flattened distribution of matter resembles foam on the void's surface, with galaxy filaments creating a web-like pattern around the empty interior. Within this cosmic cavity, the lonely spiral galaxy NGC 6503 pursues a solitary existence 17 million light-years from Earth. This dwarf galaxy, spanning approximately 30,000 light-years, displays brilliant red star-forming regions where hydrogen gas glows under intense ultraviolet radiation from newborn stars. Bright blue stellar nurseries thread through its spiral arms, while brown dust clouds in the central regions create a noble, multicolored appearance that makes NGC 6503 one of the most photogenic galaxies visible from Earth. Due to gravitational attraction from the Virgo supercluster, NGC 6503 approaches our cosmic neighborhood at 43 kilometers per second. This gradual migration toward denser regions will eventually bring the galaxy into contact with the local sheet's gas-rich environment. Astronomers predict that increased gas density will trigger enhanced star formation, potentially doubling the galaxy's stellar population over the next few billion years and causing it to shine with renewed vigor. The motion of NGC 6503 demonstrates how cosmic voids likely formed through a process cosmologists call gravitational evacuation. During the universe's early epochs, regions of slightly lower density expanded faster than average due to reduced gravitational attraction. Over billions of years, matter migrated from these areas toward higher density regions, creating an increasingly pronounced contrast between voids and filaments. Current theories trace void formation to quantum fluctuations in the universe's first moments after the Big Bang. Microscopic variations in density, imprinted during cosmic inflation, provided the seeds for all subsequent structure formation. Regions with slightly less matter became voids, while areas with marginally higher density evolved into galaxy clusters and superclusters through gravitational amplification over cosmic time. Observations confirm that most galaxies formed between 10 to 13 billion years ago, during an epoch when the universe was much smaller and denser than today. Importantly, no significant age differences exist between galaxies located in voids versus those in dense clusters. This observation supports models where large-scale structure formation began very early in cosmic history, with voids and clusters growing simultaneously rather than sequentially. Even more mysterious is the Taurus void, a 200 million light-year cavity whose detailed study remains challenging due to its location in the zone of avoidance, a region obscured by our own galaxy's disk. Bright stars and interstellar dust in the Milky Way's plane block observations of distant objects, creating a shadow zone that hides roughly 20% of the observable universe from optical telescopes. Despite these observational challenges, infrared studies have revealed the Taurus void's remarkable properties. The cavity displays an extraordinarily sharp boundary with the distant Perseus-Pisces supercluster, creating a transition zone so narrow it resembles the edge of a soap bubble. This sharp demarcation between empty space and galaxy-rich regions suggests gravitational processes operating on scales we don't fully understand. The void's apparent emptiness may be deceiving. Light passing through the torus void appears subtly distorted in ways that suggest hidden mass concentrations. Whether this represents dark matter clumping, previously unknown baryonic matter, or systematic measurement errors remains hotly debated among cosmologists. Some theories propose that voids contain vast clouds of primordial gas that never collapsed into galaxies, while others suggest exotic matter with unusual gravitational properties. Current observations have identified only 2 galaxies within the entire torus void, UGC 2627, a spiral galaxy resembling the Milky Way, and UGC 2629, an elliptical dwarf system. Both objects lie approximately 185 million light-years from Earth, separated by a few 100,000 light-years in the void's heart. Their existence demonstrates that even the most empty regions of space can harbor isolated galactic systems, though such discoveries remain extremely rare. The local group and its surrounding void structure form part of an even larger cosmic architecture. Together with 4 other superclusters, the Virgo supercluster creates a massive galactic filament called Laniakea, containing over 100,000 galaxies distributed across more than 500 million light-years. This supercluster complex flows toward a mysterious gravitational center known as the Great Attractor, located 250 million light-years from Earth in the direction of the constellation Centaurus. Laniakea itself represents just one element in an even vaster structure, a galactic stream flowing through space like a cosmic river. Surrounding this stream lie black abysses of unprecedented proportions where the light of distant galaxies drowns in emptiness so profound that even the elusive neutrinos require billions of years to traverse these cosmic deserts. The discovery of such enormous voids initially shocked astronomers who assumed the universe would be more uniformly distributed on the largest scales. Early cosmological models predicted that matter should be relatively smooth beyond distances of a few 100 million light-years, yet observations revealed structure extending to the limits of the observable universe. This cosmic architecture poses fundamental questions about the universe's formation and evolution. The existence of voids spanning billions of light-years suggests that structure formation processes operated on scales far larger than previously imagined. Some theories propose that cosmic strings or other exotic relics from the universe's birth could have shaped such massive structures, though direct evidence for such mechanisms remains elusive. Understanding void properties also provides crucial tests of cosmological models and fundamental physics. The rate at which voids expand depends sensitively on the amounts of dark matter and dark energy in the universe, making them powerful tools for constraining these mysterious components. As future galaxy surveys map cosmic structure in unprecedented detail, void statistics may reveal new insights into the universe's composition and fate. The greatest cosmic mystery. The year 2013 marked a watershed moment in cosmology when astronomer Amy Barger and her team at the University of Wisconsin-Madison made a discovery that challenged fundamental assumptions about cosmic structure. While conducting routine measurements of galactic distances using supernovae and other standard candles, they uncovered evidence for a cosmic void so enormous it questioned basic principles of cosmological theory. The discovery emerged from careful analysis of galaxy distribution patterns in our cosmic neighborhood. By mapping three-dimensional positions of thousands of galaxies within a billion light-years of Earth, the team noticed something extraordinary. Our entire local universe appeared to sit within a region of substantially reduced matter density compared to the cosmic average. Initial calculations suggested this supervoid might span nearly 2 billion light-years in diameter, larger than any structure previously discovered in the universe. The implications proved so profound that the team spent months verifying their analysis before publication, recognizing that such a finding would require revising our understanding of cosmic evolution and large-scale structure formation. Named the KBC supervoid after team members Keenan, Barger, and Cowie, this cosmic bubble encompasses not only individual galaxy clusters but entire superclusters and smaller voids within its volume. The local void, Taurus void, and numerous other previously known empty regions represent mere substructures within this greater emptiness. The Milky Way sits several hundred million light-years from both the supervoid center and its boundary, placing our galaxy in an intermediate region where void effects remain significant but not extreme. The supervoid's discovery provided an elegant solution to one of cosmology's most persistent puzzles, the Hubble tension. When astronomers measure the universe's expansion rate using nearby galaxies, they consistently obtain different values than measurements based on the cosmic microwave background radiation or distant supernovae. This discrepancy had suggested fundamental flaws in either observational techniques or theoretical understanding of cosmic expansion. The KBC supervoid explains this tension through what cosmologists call the bulk flow effect. Galaxies within low-density regions experience additional gravitational attraction from higher-density areas outside the void. This creates an extra stretching force that accelerates local expansion while leaving distant measurements unaffected. Computer simulations confirmed that such effects could account for the observed Hubble tension, resolving years of cosmological controversy. However, the supervoid's existence raises new questions about cosmic structure formation. Standard cosmological models predict that density fluctuations should not exceed certain amplitudes on such enormous scales. The KBC supervoid appears to violate these theoretical limits, suggesting either that our understanding of initial conditions is incomplete or that unknown physical processes shaped cosmic evolution. Some cosmologists propose that the supervoid represents a rare but expected statistical fluctuation, an extreme example of cosmic variance that occurs occasionally in an infinite universe. Others argue that such structures indicate new physics, possibly involving interactions between dark matter and dark energy that remain poorly understood. The debate continues as astronomers work to map void properties with greater precision. Within this vast supervoid lies an even stranger phenomenon discovered through observations of the cosmic microwave background radiation, the universe's afterglow from the Big Bang epoch. Located in the southern hemisphere sky in the direction of the constellation Eridanus, the CMB cold spot appears as a region where this relic radiation registers approximately 70 microkelvin colder than surrounding areas. The cold spot's angular size spans roughly 5 degrees on the sky, 10 times larger than the full moon's apparent diameter, making it easily the largest temperature anomaly ever detected in the cosmic microwave background. Its intensity represents nearly a 4 sigma deviation from expected statistical fluctuations, suggesting it results from real physical processes rather than random noise or measurement errors. Current theory attributes the cold spot to the integrated Sachs-Wolf effect, where CMB photons lose energy while traversing cosmic voids. As these ancient photons climb out of gravitational potential wells associated with large-scale structure, they become slightly redshifted and appear cooler when they reach Earth. This mechanism can account for temperature variations of several microkelvin across the sky, providing a natural explanation for void-associated cold spots. However, the observed cooling in the Eridanus cold spot exceeds theoretical predictions by factors of 3 to 4. Even if a massive supervoid existed in that direction, which observations confirm, the integrated Sachs-Wolf effect can explain only about 25% of the observed temperature depression. The remaining 75% of the effect requires additional physical mechanisms that remain unknown. Speculative theories propose increasingly exotic explanations for the anomalous cooling. Some models invoke interactions between dark energy and dark matter that could amplify temperature fluctuations beyond standard predictions. Others suggest that the cold spot might represent a collision site between our universe and another in a multiverse scenario, where different physical laws or cosmological parameters could create observable signatures. Even more radical proposals include variations in fundamental constants across cosmic distances, primordial black holes with exotic properties, or topological defects left over from phase transitions in the early universe. While such ideas remain highly speculative, they illustrate how the cold spot continues challenging our most basic assumptions about cosmic uniformity and the laws of physics. The mystery deepens when considering the cold spot's relationship to the KBC supervoid. The angular position of maximum cooling appears offset from the supervoid center, suggesting either that multiple structures contribute to the observed effect or that unknown processes redistribute the temperature signature across the sky. Future observations may clarify whether these phenomena represent related aspects of the same underlying cosmic architecture. Advanced theoretical modeling attempts to reproduce the cold spot's properties using sophisticated simulations of cosmic structure formation. These calculations incorporate dark matter-particle interactions, varying dark energy equations of state, and modified theories of gravity that could enhance large-scale structure growth. So far, no model successfully explains all observed characteristics while remaining consistent with other cosmological constraints. The cold spot represents more than just an observational curiosity. It provides a unique laboratory for testing fundamental physics under extreme conditions impossible to replicate on Earth. Its properties encode information about dark matter particle masses, dark energy evolution, and possibly even the topology of spacetime itself. As observational techniques continue improving, this cosmic refrigerator may yield insights that revolutionize our understanding of the universe's most mysterious components. Echoes of creation. The cosmic voids that dominate universal structure may ultimately prove more important than the galaxies and stars that capture our attention. These seemingly empty regions encode information about the universe's birth, evolution, and ultimate destiny. They serve as cosmic laboratories where physicists can study dark matter and dark energy under conditions that span billions of light-years and cosmic epochs. Recent theoretical developments suggest that void properties provide unique windows into the physics of cosmic inflation, the hypothetical period of exponential expansion that shaped the universe's earliest moments. Quantum fluctuations during inflation created the density variations that eventually grew into the cosmic web, with voids representing regions where these primordial perturbations had negative amplitudes. Computer simulations reveal that void evolution depends sensitively on the nature of dark energy and its interactions with dark matter. If dark energy behaves as a simple cosmological constant, voids should expand at predictable rates determined by the universe's overall expansion. However, if dark energy varies with time or interacts with other cosmic components, void growth patterns could deviate from standard predictions in observable ways. Future astronomical surveys will test these theoretical predictions with unprecedented precision. Projects like the Euclid Space Telescope, the Vera Rubin Observatory's Legacy Survey of Space and Time, and next-generation radio telescopes will catalog billions of galaxies and map void boundaries with exquisite detail. These observations may finally reveal whether cosmic voids conform to theoretical expectations or contain surprises demanding new physics. The statistical properties of void populations provide particularly powerful cosmological tests. Standard models predict specific distributions of void sizes, shapes, and density profiles that depend on fundamental parameters like the dark matter particle mass and the dark energy equation of state. Deviations from predicted patterns could indicate unknown physics or reveal systematic errors in current cosmological models. Some researchers propose that cosmic voids might concentrate exotic forms of matter with properties we haven't yet discovered. Rather than being truly empty, the largest voids could harbor regions of antimatter, particles with negative mass that repel rather than attract ordinary matter, or even interdimensional connections to parallel universes. While such ideas remain highly speculative, they remind us that 95% of the universe consists of dark components whose properties remain almost completely mysterious. The possibility of negative mass deserves particular attention, as it could naturally explain both cosmic acceleration and void formation through a single mechanism. If regions of space contained matter with gravitationally repulsive properties, they would naturally expand faster than average and create the void structures we observe. However, no laboratory experiments have ever detected particles with negative mass, and theoretical arguments suggest such matter might violate fundamental physical principles. Alternatively, cosmic voids might provide evidence for modified theories of gravity that could eliminate the need for dark energy entirely. Some proposals suggest that Einstein's general relativity breaks down on cosmic scales, with gravitational attraction weakening over distances exceeding hundreds of millions of light-years. Such modifications could naturally explain cosmic acceleration while predicting specific patterns of void growth and evolution. The study of cosmic voids also illuminates the universe's ultimate fate. If dark energy continues accelerating cosmic expansion, the voids will grow exponentially larger while galaxy clusters become increasingly isolated. Eventually, even-bound structures like galaxies and solar systems could be torn apart by runaway expansion, leading to a cold, empty universe where individual particles drift through infinite space. However, alternative scenarios remain possible. Some theoretical models predict that dark energy could decay or reverse its effects over cosmic time, potentially causing cosmic expansion to slow or even reverse into contraction. In such scenarios, the current epoch of void growth might represent a temporary phase in cosmic evolution, with future eras characterized by structure collapse and universal compression. Recent observations hint that void properties may violate expectations in subtle but significant ways. Light passing through the largest voids appears distorted in patterns that suggest hidden mass concentrations or unusual gravitational effects. Whether these observations represent dark matter clustering, previously unknown baryonic matter, or measurement systematics remains hotly debated among cosmologists. The resolution of these questions may require new observational techniques that can probe void interiors directly rather than relying on boundary measurements. Gravitational wave detectors might eventually become sensitive enough to detect signals from exotic processes occurring within cosmic voids, while neutrino telescopes could reveal high-energy phenomena invisible to conventional astronomy. The infinite question. As we peer deeper into space and further back in time, each discovery expands our conception of what's possible in nature while simultaneously revealing the profound limitations of human knowledge. The universe revealed by modern astronomy proves far stranger, more beautiful, and more mysterious than our ancestors could have imagined, yet every answer we discover opens new questions that challenge our fundamental understanding of reality. The cosmic voids that dominate the universe's large-scale structure represent more than mere empty space. They encode the history of cosmic evolution from the first moments after the Big Bang to the universe's ultimate fate billions of years in the future. These seemingly barren regions may harbor the keys to understanding dark matter, dark energy, and the fundamental forces that shaped cosmic destiny. From Pluto's hidden ocean to the KBC supervoid that encompasses our entire cosmic neighborhood, modern astronomy has revealed a universe operating on scales and through mechanisms that dwarf human experience. Neutron stars spinning hundreds of times per second challenge our understanding of matter under extreme conditions, while black holes demonstrate how gravity can become so strong that space and time themselves break down. The bizarre exoplanets discovered beyond our solar system, worlds that vanish and reappear, planets locked in gravitational death spirals, and gas giants surrounded by ring systems larger than planetary orbits, remind us that the cosmos contains possibilities we never anticipated. Each new discovery forces astronomers to expand theoretical models and confront assumptions about planetary formation and evolution. Perhaps most humbling is the realization that despite centuries of scientific progress, we have barely begun to comprehend the universe's true nature. The visible matter that forms stars, planets, and galaxies represents only 5% of cosmic content, while dark matter and dark energy, components we can detect only through gravitational effects, dominate universal evolution through mechanisms we don't understand. The greatest mysteries may still await discovery. Just as early astronomers couldn't have imagined quantum mechanics, relativity, or cosmic expansion, we may be blind to phenomena that future generations will consider obvious. The universe has consistently proven more complex, more interconnected, and more surprising than human imagination alone could conceive. Current theoretical physics stands at a crossroads where quantum mechanics and general relativity, our two most successful theories, remain fundamentally incompatible. The resolution of this conflict may require revolutionary insights that transform our understanding of space, time, matter, and causality. Cosmic voids and other extreme astrophysical environments provide natural laboratories for testing such theories under conditions impossible to replicate on Earth. The search for extraterrestrial life adds another dimension to cosmic exploration. As astronomers discover potentially habitable exoplanets around nearby stars and evidence for subsurface oceans throughout the solar system, the possibility grows that life may be common in the universe. The detection of extraterrestrial organisms, whether microbial or intelligent, would revolutionize our understanding of biology, evolution, and our place in cosmic history. Future technological advances promise to extend human reach throughout the cosmos. Space telescopes with unprecedented sensitivity will probe the atmospheres of distant exoplanets for biosignatures, while gravitational wave detectors will reveal cosmic phenomena invisible to electromagnetic astronomy. Robotic missions to the outer solar system may discover life in the hidden oceans of icy moons, fundamentally altering our perspective on biological possibility. The ultimate questions raised by cosmic exploration transcend science itself. Why does the universe exist at all, rather than nothing? Why do the fundamental constants of physics have values that permit complex structure formation and the emergence of life? Are there other universes with different physical laws, and if so, what principles determine which realities become actual? Our journey through the cosmic unknown reveals that we inhabit a universe of infinite wonder, where every discovery illuminates new horizons of mystery and possibility. The adventure of cosmic exploration represents more than scientific investigation. It embodies humanity's deepest aspirations to understand our origins, our destiny, and our significance in the grand cosmic story. In confronting these cosmic mysteries, we discover not just the nature of the universe but the remarkable capacity of human consciousness to reach beyond itself and touch the infinite. We are atoms forged in stellar cores, contemplating the very cosmos that created us. In this profound sense, the universe becomes conscious of itself through our scientific investigations, making cosmic exploration an act of cosmic self-discovery. The greatest adventures lie ahead as humanity expands beyond Earth and begins exploring the cosmos directly. Future generations may walk beneath alien skies, probe the event horizons of black holes, and travel between the stars. Each step in this cosmic journey will reveal new wonders and deeper mysteries, ensuring that the exploration of the unknown will continue as long as conscious beings seek to understand their place in the infinite cosmos. The universe awaits, vast and mysterious, filled with secrets that challenge our imagination and expand our conception of what's possible. The journey through cosmic mystery has only just begun, and the most profound discoveries may lie ahead in realms we have yet to imagine. In reaching toward these cosmic horizons, we participate in the greatest adventure ever undertaken, the quest to understand our universe and our place within its infinite wonder.